Assalamu alaikum, dear students. In today's session, we'll explore one of the most fundamental optimization problems used in decision making. That is assigning tasks efficiently while minimizing costs or maximizing efficiency. And such type of models are called assignment models. An assignment model is a special case of a transportation problem where we aim to assign a set of tasks to a set of agents like workers, machines, or jobs in the most optimal way. Each assignment has an associated cost, and our objective is to minimize the total cost or maximize efficiency. So, such models occur uh, in case of workforce allocation, production scheduling, project management, or sports team selection, etc. And in order to solve, there are several methods we have in literature, like Hungarian method. This is an efficient algorithm for solving such problems optimally. We can also solve these problems with the help of graphical representation using network diagrams. And these models can also be solved by constructing linear programs with the help of any variant of simplex method. But in this video, we are going to learn Hungarian method, and specifically we'll learn minimization case in this video. So in order to learn the method, let's have an example. So we'll learn by doing this example. And in this example, a company has 4 jobs to be completed using 4 machines. Each machine must be assigned to complete one job. Right? So this is important information. The time required to set up each machine for completing each job is given in this table. Company wants to minimize total setup time needed to complete the 4 jobs. So time here is time spent by a particular machine to do some job is cost in this case. So we are going to minimize times, that is our cost here is the time uh, specified for a machine to do a job. And lastly, we are required to use Hungarian method to solve the problem. So let's start solving this. So first of all, we need to have a cost matrix. So this is the cost matrix. That is the machine A does job 1 in 14 units of time. Similarly, machine B completes the job 4 in 5 units of time, and so on. You can read this data like this. Okay, so first step of Hungarian method is to find a basic feasible solution, and this step 1 consists of 2 sub-steps. In first step, we find minimum element in each row of m by m method, that is a square method. This is also important to make sure that our cost matrix is a square matrix. If this is not a square matrix, the system is called unbalanced system, and we have to make it a balanced system by inserting a dummy job or dummy machine or dummy worker or dummy whatever, wherever is needed, we are going to add dummy row or dummy uh, column. So let's get back to the step 1. Find minimum element in each row of this cost matrix. That is, we have 4 rows, so we have to find minimum element of each row. Like in this case, we have 5. In row B, we have 2. In row 3, minimum element is 3. In row D, minimum element is 2. Now, what to do with these elements? Let's see. Construct a new matrix by subtracting from each cost of the minimum cost in its row. That is, we have to subtract 5 from each of the elements in row A in order to have a row reduced matrix. So let's see what happens if we do that. This is the resulting matrix. 14 minus 5 is 9. 5 minus 5 is 0. 8 minus 5 is 3. 7 minus 5 is 2. Similarly, 2 minus 2 is 0. 12 minus 2 is 10. And 6 minus 2 is 4. 5 minus 2 is 3. And 7 minus 3, this is the least element, so 7 minus 3 is 4, 8 minus 3 is 5, 3 minus 3 is 0, 9 minus 6 is 9 minus 3 is 6. So in this case we are going to subtract 2 from each of the element in this row. So we have 0, 2, 4, 8. Okay, so next step of step 1 is to find minimum element in every column in the new matrix. So this is the new matrix. Now we are going to find out minimum element in every column. So column 1 we have 0, and in column 2 0, in column 3 minimum is 0, in column 4 minimum is 2. So now we will subtract this minimum element from each element of the corresponding column. So since column 1, 2, 3 have minimum 0, so they will remain unchanged, and in column 4 we have a non-zero minimum, that is 2. So after subtracting 2 from each of the elements in column 4 we have this matrix. So this is column reduced matrix, and this is called reduced cost matrix, right? So this is called reduced cost matrix. So once we have reduced cost matrix, we'll try to allocate machines to jobs. So wherever we have 0, we can try an assignment. So let's do that. And if we are not able to assign, then we'll move to the next step. So we can see that we can assign machine A to complete job 2, machine B to do job 1, machine C to do job 3. So in the row A, B, C, let's cross rest of the zeros if we have some other zeros. Okay, in row D, there is no option to assign the job, because the only option machine D can be assigned is job 1, but this job has already been assigned. So our problem was to assign one machine to do one job, right? So this is the row which is unassigned. So let's see what to do next. And next step is draw minimum number of lines, horizontal or vertical, that are needed to cover all zeros in the reduced cost matrix. If assignment is not done, then we are going to do these steps. So in this case, number of lines required to cover all the zeros must be less than the order of the matrix. If this is equal to the order of the matrix, then we are done. We should have an optimal assignment. We should have an optimal assignment. But if we don't have an optimal assignment, then a number of these lines, these vertical or horizontal lines covering all the zeros must be less than the order of the matrix, cost matrix, right? Okay, so let's try. So this is the assignment done part. Okay, now there are few things to take into account while covering these zeros by vertical or horizontal lines. So first step is to mark all the rows with no assignments. So we only have one row which has no assignments, this. So let's mark this. Okay. Step 2, for each row just marked, that is only this one, mark each column that has a 0 in that row. So this row has 0 here, that is mark this column. Okay. For each column, just mark each row that has an assignment in that column with this tick. Okay. So in this column, this row has an assignment, so this is marked. Okay. Now you have to cover, now let's try cover these. So you have to cover this marked column first of all, and then cover all unmarked rows. So this is how you can cover all the zeros with minimum number of lines. Okay. I hope it makes sense. Now let's uh, move to next step. Okay, so find the smallest. Now once all the zeros are covered by vertical or horizontal lines, so find out smallest non-zero element. So this is important. In this case, you need to find out smallest non-zero, and there will be smallest element. Smallest element should be non-zero because all the zeros are covered. So smallest non-zero element that is not covered, okay, in reduced cost method, that is uncovered. So in this case, we have 1. Now subtract this element, this smallest element, which is uncovered, from all of the uncovered elements, right? From all of the uncovered elements, and add this to the elements covered by 2 lines like this and this. So subtract this one from 10, 4, 2, 4, 6, and add this one to 9 and 4. Right? So let me read again. Subtract this smallest element from each uncovered element of the reduced cost matrix and add to each element that is covered by 2 lines. Okay. So our resulting matrix would be this. So 9 plus 10, 4 plus 1, 5, and 10 minus 9, 4 minus 1, 3, 2 minus 1 is 1, and this is 4 minus 1 is 3. So again, we'll try to make an assignment. If we are able to have an optimal assignment, we are done. Otherwise, we have to repeat these steps again. Okay, let's try. So we have this assignment for machine A, that is machine A should do job 2. Machine B can complete job 1, and machine C can complete job 3. Similarly, machine D, and there is a tie, so we can assign job 4 to machine B, and this is how we are able to assign one machine to one job. So assignment is done. So this is the assignment matrix, and we can write optimal solution as machine A will do job 2, machine B will do job 4, machine C will do job 3, and machine D will complete job 1. Now, in order to find the minimal cost and optimal solution, we have to look into this matrix. So if machine A completes job 2, that is, its cost is 5, right? And if machine B completes job 4, cost is again 5. So machine C completes job 3, its cost is 3. And machine D completes job 1, so cost. So total cost would be 15. So this is the optimal solution. So that is all. Take care. Bye.